Okay, so for part 4, graphing sine, cosine functions. A couple little housekeeping things first that I wanted to talk to you guys about. Up here and go. So, as far as the grades remaining in the 9 weeks, I know a lot of people were holding out hope that somebody was going to swoop in and say nobody can fail. Guess what? It didn't happen, as I predicted. So the grades will stand for this 9 weeks and for this semester. Grades remaining for this class. So this is a Friday. You're going to have 4 homework. And I'm also going to open up the quiz. So you're going to have a quiz and a homework that I'm going to open up in Google Classroom today. They'll both be due Monday. And then you'll have 4.5. And then 4.6 and 4.7, I'm going to make, I'm going to put both of those out in one day. And then on Wednesday, we're going to have the chapter 4 test. So that's it. That's all that's left in the 9 weeks. These two, the quiz and the test, can have the largest impact on your average. You ace those and do really well. And the quiz, there's no reason why you shouldn't. I've made it as simple as possible and still cover the material. But anyway, you've got those 4 homeworks, 1 quiz, 1 test. That's it for the 9 weeks. Make sure you do well on that. And Parent-Teacher Day is, of course, tomorrow. I have contacted directly the parents of all students that were failing, either by email or phone or whatever. I've also given that student a document. So if you haven't got one, you know that you're not failing. Okay, so 4.4, graphing sine and cosine functions. Do you guys have a go-to doodle? You know, something you draw on the margins of a paper whenever you're bored, or maybe at is that kind of a thing of the past, I guess? The new doodle is the phone, I suppose. Anyway, back in my day, when we were bored, we would doodle on paper. And this is one of my favorite doodles, the sine and the cosine function. So we're going to graph those and their transformations, and we're going to use a sinusoidal function to solve a problem. First of all, a sinusoid is a times the sine of bx plus c as the argument, and then plus d outside the argument. So this is a transformed sine function, and you can also use cosine. So a times cosine of bx plus c in the argument, and then plus d outside the argument. A and b must not be 0. Those are the only rules for the parameters. So sine of bx plus c, a times sine of bx plus c plus d. It's called a sinusoid. And whether you use the sine or the cosine, it still falls under the sinusoid name. All right. So the amplitude is the distance a function deviates from its midline. So if you have a periodic function, in other words, a function that repeats, how far it goes away from its midline is called the amplitude. You notice I've given you a handy graph here. The frequency is how often a period occurs. So, you know, like with light, for example, with an electromagnetic wave, we perceive different frequencies as different colors. Outside of our visual spectrum, frequency impacts things like how the wave propagates over distances, whether or not it can penetrate things. For example, X-rays are real good at penetrating things, visible light is not. It's a consequence of their frequency.
What does that say? How
often a period occurs.
Would you use this stuff if you're studying what kind of waves?
Indeed, yeah. And music, we perceive different vibrations in the air as musical notes. And it's a consequence of the frequency of those vibrations, the different notes we perceive. So frequency plays an outsized role in our interactions with the physical world. Phase shift, that's just a horizontal translation. So when I say phase shift, I just mean moving it to the right or left. And these last two are pretty intuitive. The vertical shift is the vertical translation, up or down. And the midline is the center, if you will, of the graph. So imagine if you averaged all the values of a periodic function, wherever that would land on would be considered its midline. Guys good? Okay, so these are some properties of the sine and cosine function. I'm only really concerned that you memorize what I've got here. The rest you can consult as needed. So the domain is all real numbers for both. The range is -1 to 1, including both bounds for both. And the period for both is 2 pi. So the sine and the cosine share these three characteristics. They're going to be important to us when we graph them. The rest of this, not so much. Domain, range, and period are the most important values when you're graphing a function. Okay, so without further ado, let's graph these. We'll start with the sine of X. So with my axes here, I want to go at least 2 periods worth of the graph. Make sure that's roughly in the center. Does appear to be. So what is my period for the sine function, Rowdy?
2 pi.
Very good. So if I go from -2 pi to 2 pi, you see how that's going to be 2 periods? And then we'll logically separate it. That last one I don't like so much. Wow. You really going to leave that one? Okay. There we go. And in order to find these points, and the range values have to be between -1 and 1. So I don't need a whole lot of range. -1 to 1 is just fine. So for putting these points in, I'm going to use the unit circle. So you'll remember we discussed the unit circle, and we had some points on here. So first of all, 1, 0. So that corresponds to the angle 0. And the x-axis here is the angle in radians. And the y is, of course, the sine of x. So if I put in 0, then the output is going to be the y-coordinate from the unit circle, which is also 0. So the origin is a point in this graph. And then if we go up to pi over 2, I have 0, 1. So at pi over 2, it's 1. And if I come over here to pi, -1, 0. The y-coordinate is the sine. So that is, again, 0. If I go to 3 pi over 2, which is this next tick mark, I have 0, -1. So we're at -1. And then if I go back to 2 pi, I am back to 0. So the right side of the graph, you need to connect these points with a smooth curve. So let's do that. Make that curve smooth. Now let's do the points on the left side. So we're moving in a negative angular direction when we go to the negative values here. So first of all, negative pi over 2 is here, so that's -1. I'll use black for the points. And then negative pi, you're at 0. -3 pi over 2, I'm back to here. And so that's +1. And then -2 pi, right back where we started at 0. Once again, let's connect those points with a smooth curve. So if you remember the unit circle, there's no excuse not to be able to graph the sine function. A logical question presents itself here. Can my calculator do this? Yes. It's fun to do it by hand, so I don't know why you would avoid such a fun exercise, but if for some reason you wanted to, you can put in sine of x, but you have to be careful that a few things are true. First of all, your mode has to be in radians. So when you graph a trig function, your mode needs to be in radians. Make that mental note. Graphing trig function equals radian mode. And then we need to set our window to go from -2 pi to 2 pi. And then let's go -1.5 to 1.5 on the y. Be careful not to rely overtly on your calculator, because this really neatly combines a lot of skills that I've taught you in this chapter. It's a really good way to reinforce the things that I've taught. So if you just hit a button on a calculator, it doesn't do that. Now let's talk about the cosine of x. So for the cosine of x, we'll use the same x and y's. So this is the angle in radians, and y is cosine of x. We'll go from -2 pi to 2 pi, and from +1 to -1 is fine for the range. We want to subdivide this logically. So we're going up by pi over 2 each time. Once again, we're going to consult that good old unit circle. The quadrantal angles are the ones we're concerned about. So those are all we need to know to graph this effectively. First of all, cosine of 0 is 1 this time. So the cosine of x does not pass through the origin unless it's transformed in some way. So cosine of 0 is 1. Remember, we're looking at the x coordinate this time. Pi over 2, which is this tick mark, is 0. Pi, which is this mark, is -1. And then 3 pi over 2 is 0. 2 pi, we're back to +1. For negative pi over 2, which is here, we're at 0 for the x coordinate. For negative pi, we're at 180. So that's -1. For negative 3 pi over 2, we're all the way back to here. And so that's for the x coordinate, 0. And then negative 2 pi, you get right back to where you started. So you're at +1. And then we'll connect these points with a smooth curve. That's the cosine. All right. The calculator, can it do the cosine? Yes. But it's boring. It's more fun to do it yourself. Okay, so this tells you how the cosine works. The x-axis is the angle that we're inputting. Hold on, make sure you're not distracted, my man.
Oh, I'm on.
Okay, I got you. Looking at your lap, you make me nervous. Although I know your phone is destroyed, so I guess I shouldn't have thought you would.
It's like half-baked.
Okay, so the amplitude of a sinusoid is just A, the absolute value of A. So what you need to know here is if you have a sinusoid, which you've already wrote down the formula for the sinusoid, the amplitude of that sinusoid is going to be the absolute value of the A term. So the absolute value of the A term is your amplitude, how far it deviates. So amplitude represents the strength of a wave. And you remember I said frequency determines its characteristic. You know, like is it an X-ray? Is it visible light? The amplitude determines how strong it is. So you could have waves that carry much more energy, and that would be in the form of a greater amplitude. Whether the sound is loud or not is a consequence of its amplitude. The note is a consequence of its frequency. So you can make a low note that's really loud, like, and that has both a low frequency and a high amplitude. So, and that's the case for, like I said, in many ways we interact with our physical world. So let's describe two graphs, sine of x and 2.5 times sine of x. We're going to sketch both functions on the same axis. And two periods, it says. So we've got f of x equals sine of x. So we need 1, we need 2, and we need 3 in this case. So first of all, for the sine of x, we already know how that works. We just graph this bad boy. And then we do a smooth curve, of course. So there's sine of x. 2.5 sine of x. Well, for this, the amplitude is 1. But for 2.5 sine of x, the amplitude is going to be 2.5. So all the zeros will be shared, but every place where the function is at its max or min, instead of going 1 unit from the midline, it's going to go 2.5 units from the midline. So again, the zeros are shared because 0 times 2.5 is still 0. But everywhere where it has a max or a min, instead of 1 unit, it's going to deviate from the midline by 2.5 units. And we'll graph this on the calculator. It's always a good idea to confirm your results. I need to change my window to go from -3 to 3. And we've got sine of x and 2.5 sine of x. So there's the red line on my graph, the sine of x. There's the green line on my graph, the sine of 2.5 times the sine of x. Kind of like the Star Trek logo, doesn't it? Old video game designers used to have to use all kinds of interesting formulas to replicate insignias and so forth. Anything they wanted to include in the game had to be defined mathematically. Nowadays, you have integrated development environments. So you just tell it what you want and the computer does the formula for you. You know, SketchUp and Blender and all that. The mathematics is incidental. It's taken care of. Okay, so on this one, sketch for me the graph of cosine of x and 5 times the cosine of x really quickly. I'll give you about a minute to do that. Shouldn't need much longer. Use your calculator to check your work. You've done a sketch. About another 30 seconds. Good. So what you should have found is the following. The cosine of x, and actually I don't have enough y here. Let me change my window. You want to go further than the amplitude of the function on your graph. So there's the cosine of x, going up 1 unit and down 1 unit, and here's 5 times the cosine of x. Shares the zeros, but the amplitude is increased from 1 to 5. All right. So what about cosine versus -2 cosine x? So we've got 2 transformations taking place. First of all, it is flipped over the x. Second of all, the amplitude is increased to 2. We used to call that a vertical stretch. and it still is, but in terms of trigonometry, it's referred to as amplitude. So let's sketch the cosine of x. Okay, so remember with the cosine, started at 1 and went down. Like so. So let's connect those with a smooth curve. For -2 cosine of x. So first of all, let me change that to red line because I wrote the name of it in red. It would make more sense that way. And then I'll do the transformation in black. So every 0 is going to be shared because -2 times 0 is still 0. But all of the points will be flipped over the x-axis and expanded amplitude to 2. Like so. Let's test our result here on the good old calculator. This time I'll change it to go from -3 to 3. It's good practice changing the window this frequently. So cosine of x compared to -2 times cosine of x. So there's the red line, cosine. And second would be the black line. Looks like a bunch of eggs or something. Okay, questions about that? All right.
So it flips because it's the negative, right?
Mm-hmm. Yeah, the negative is what causes us to flip over the x-axis. Good question, Rachel. Okay, so the period of a sinusoid is going to be the original period, and I don't write 2 pi here because for the tangent and cotangent, the period is not 2 pi, but the original period, in other words, the period the function has when it's unmodified, divided by the absolute value of b. And in the case of the sine and the cosine, that's 2 pi divided by the absolute value of b, whatever our b parameter is. So it will modify our period. Okay. So we've got cosine of x and cosine of x divided by 8. So our b value here think about if I wrote this as, a times the cosine of bx plus c plus d. See how this would be 1 for the a parameter, and then 1 over 8 for the b parameter, and then both c and d would be 0. So our b value is 1 over 8, and as a consequence, our period is 16 pi. Now this is going to be a super busy graph, because if I graph cosine from -16 pi to 16 pi, that's going to be a lot of up and down action. So we'll use the calculator for that rather than spending 20 minutes on it. Cosine of x, and then the cosine of x divided by 8. And this time, if we want 2 periods of this function, we need to go from negative 16 pi to 16 pi, because that's its period. And then that's okay for the y. So look at cosine. See how busy he is? Like a static interference pattern. But that's because this one has a period of 2 pi. This one's 16 pi. So this one is going to occur 8 times as frequently. So for every 1 period of the modified function, you have 8 periods of the original function. Let me change that to be a fat line for the g of x. So again, this is the original function. And there's our modified function. Questions about that? So this would be like, the first one would be like blue light, and this one would be like red light. All right. So this is their representation. So here's one, and again, we'll just do this one by calculator. So sine of 4x has a b value of 4, and so its new period is going to be 2 pi divided by 4, which is pi over 2. So the original function between negative 2 pi and pi will have 2 periods, but this one will have 4. So in this case, the modified version is going to be the busy one. So sine of x, and then sine of 4x. I've got too much y. I need to go. And it makes you go through the whole thing. Yeah, we need to go from negative 2 pi to 2 pi in this case. You just need 2 periods of each function. So you pick a value for your window that makes that happen. So we had to pick negative 2 pi to 2 pi to get 2 periods of the second function. I'm sorry, the first function. Second function is the one that's so busy in this case. So that's an example of period modification. The b value determines how many periods happen over a given portion of the domain. So frequency, here's something that, as far as the pure mathematics of trigonometry go, we don't use very often, but in applied trigonometry, like I said, the analysis of light, of music, or any of the waves that propagate, and according to string theory, like everything's a wave and also a particle. But anyway, when you analyze the physical world, frequency is a big old deal. And it is 1 divided by the period. So the frequency of any sinusoid is 1 over its period, which is the absolute value of b over 2 pi in the case of a sine or a cosine. Because for a tangent, we would not be using 2 pi, but we'll worry about that tomorrow. Not tomorrow, but next lesson, Monday. So frequency is 1 divided by the period. So a bass tuba can hit a note with a frequency of 50 cycles per second and an amplitude of 0.75. Write an equation for a cosine function that can be used to model the initial behavior of the sound wave associated with that note. So this tells us the A value is 0.75. This tells us the absolute value of B divided by 2 pi equals 50. So if I multiply both sides by 2 pi, I get the absolute value of B equals 100 pi. And so we'll take the positive value here. I'm not concerned about the negative in this case, even though it would describe it in the same way. So we're going to say f of x equals a times the cosine of bx plus c plus d. We're going to set c and d equal to 0 in this case. 0.75 times the cosine of 100 pi x. Would describe that sound wave as it propagates. You would really need a dampened trig function to describe this most accurately, because as the sound wave propagates, it's going to diminish in amplitude. Its amplitude will not remain constant. You can't blow a tuba and it's heard on the other side of the universe. It would slowly, its amplitude would slowly approach 0 as it propagated. All right, so I don't think we need another one of those. Phase shift. Phase shift is negative c divided by the absolute power of v. This is the horizontal translation. And be careful in your book, because for some reason that negative sign looks like part of the fraction mark, but it is negative c divided by the absolute power of v. And of course, we're talking about the c parameter from the sinusoid. Let me know if you guys have any questions. All right. Phase shift, leftward or rightward movement. So here's one. State the amplitude, period, frequency, and phase shift of the following. Then graph 2 periods of it. So the amp is going to be 2. It's the absolute value of 2. The period is going to be 2 pi divided by that absolute value of b, which is 5. So that's 2 pi over 5. No simplification necessary. And then the phase shift, well, frequency is next. So the frequency is going to be 5 over 2 pi. And then the phase shift. So the phase shift is going to be negative c over the absolute value of b. So that's negative pi over 4 divided by 5, which is going to be negative pi over 20. Multiply top and bottom by 4 here to get this result. Okay, so let's graph 2 periods of it. We'll use the calculator for this, otherwise it would be a really tedious exercise. I can find a bunch of points and stuff. So 2 times the sine of 5x plus pi divided by 4. And I'm going to go to my window, and I need 2 periods. So I want to go from negative 2 pi divided by 5 to positive 2 pi divided by 5. So it's going to give me 2 periods. The amplitude is 2, so the negative 3 to 3 will work perfect. All right, let's graph it. You notice it won't be symmetric about the y-axis in the way the previous ones were, because it is phase shifted a little bit. That's that negative pi over 20. It's phase shifted just a touch. Okay, any questions about anything? Vertical translations are fairly trivial. You know, you just take the whole graph and you shift it up or down. There's no complex formulas here. The vertical shift is just going to equal that d value. So in this case, it's 1. So the amplitude of sine of x plus pi plus 1, like this, is going to be 1. It's the number that is out here in front of sine, and in this case there's none, so it's understood to be 1 times that amount. the period is going to be 2 pi divided by b. In this case, the b value is 1 as well. So that's just 2 pi. Our phase shift is negative c, so that's negative pi, divided by b, which is 1, or absolute value b, which is 1. So the phase is negative pi. And then the vertical shift.
Well, how do you get negative pi then?
Positive 1. So the phase shift is negative c over the absolute value of b. I identified the c parameter here as pi. The b value is 1. So negative pi over the absolute value of 1 is just negative pi. Good question, Rachel. And then they also want the frequency. So you just invert the period for that. So amplitude is 1, period is 2 pi, frequency is 1 over 2 pi, phase shift is negative pi, and vertical shift is positive 1. So they say graph 2 periods of this. So sine of x plus pi plus 1. And I want to go from negative 2 pi to 2 pi. That's 1 period in each direction. Notice it's not going to be symmetric around the x-axis this time because we're shifted upward. All right, we're getting there. Questions about anything so far? So vertical shift is d, and the midline is y equals d. So the only thing on this page we haven't discussed so far is the midline is going to be y equals d. This graph is on one of the pages in this chapter. I forget which page. But anyway, if you need these formulas all together in one place, look for this section in your text. Okay, and now possibly one of the more challenging problems in this whole chapter. We're tasked with modeling data using a sinusoidal function. So, and notice this font is really small because I had to try to fit all that on there. This is a calculator problem. So the tides in the Bay of Fundy in New Brunswick, Canada. Wonder if that's an Indian name, Fundy. It's hard to say. Have extreme highs and lows every day. So you guys know how tides work. Myrtle Beach, if you go out in the morning, the water is retreated quite a bit. If you go out in the evening, it's up quite a bit, and so forth and so on. And so that varies over different areas. Some places have a greater high and low tide. It's a consequence of the moon. The moon is sometimes closer and sometimes farther away. That's called its apogee and perigee. The table shows the high tides for 1 lunar month. Write a trig function that models the height of the tides as a function of time x, where x equals 1 is the first day of the month. So we're going to use a cosine model because we want our first value to be a high, looks like. Yep. So you see how this is greater than the ones that follow it? And yeah. And so this is one of the peaks. So the cosine model makes more sense here. So we're going to use a times cosine of bx plus c plus d. So if we put this data in our calculator, so stat, edit, clear out whatever's in there, and prepare to punch buttons for a hot minute. So it's 1 through 30. Careful not to make mistakes, or you're just going to start over, and that's a whole big worse than taking your time. Trust me. All right, now we go over to L2, and we'll put in the tides. It'll be real easy to mess these up. Yeah, and if you're working this problem with a friend, the one I'm going to give you on the homework, and you all get a slightly different answer, that's okay. Calculators use a slightly different algorithm sometimes. Okay, so if we go to the home screen and then stat and calculate the sine reg down here at the bottom. Which it'll have to think about for a hot minute. So this is using a sine model. We're using a cosine model because we want it to start, but it will share all these values. So A is 1.7. And then B is 0.36. Yeah, your calculator can't do cosine stuff. But hopefully it shouldn't make much difference. We'll test it and see. C equals about 1.6. And then actually the C value is where we're going to find some differences. I think our C value will just be 0 for the cosine, but we'll experiment with that. D equals about 25.5. So let me try this, the function they found. So if we go to VARS, statistics, equation, and regression equation, and then we'll go up here and turn that plot on. And then I'm going to set my window up. I want to go from -1, let's say, to about 30. Well, let's go to about 50. So that way we have way beyond the end of our data here. And the Y values go from, they stay in the 20s. So let's go from like 0 to about 35. So there's our data, and there's our function, modeling it quite well. See what happens if we go to cosine and we change the C parameter to 0. Yep, that's it. So if I want to use cosine, I would just make this C value 0. Boink. Okay, so questions about this? All right, in that case, I declare part 4 complete. And your assignment, along with your quiz, will be posted very shortly on Google Classroom. Make sure